Welcome. This is going to be a vodcast on reaction mechanisms. Reaction mechanisms are basically the steps of how a chemical reaction occurs. We've kind of accustomed to a chemical reaction where we know what the reactants are, we know what the products are, but we are now going to look at exactly how that happens. And sometimes some things get formed that are not shown up in a chemical reaction, but it's definitely formed and consumed in the steps. So a balanced chemical equation does not tell us a mechanism. So just to kind of relate this, take for example the classic example of making peanut butter and jelly sandwiches. So here I have my reactants, peanut butter, jam, and two slices of bread, and it forms my PB&J. So here's my little chemical equation. I know exactly what my reactants are, and I know exactly what my product is, but nowhere in this chemical equation does it tell me in what order am I making this sandwich. Do I put the jelly and the peanut butter together first and then put it on the bread? Do I put the jelly on first or do I put the peanut butter on first? I don't know. So that is what a reaction mechanism is. It is now going to define exactly what's going on in a chemical equation. So let's go with an example here. Okay, so here we have an example of nitrogen dioxide gas reacts with carbon monoxide to form nitrogen monoxide and carbon dioxide. So chemical equations right here. It was determined by experiment that the rate law, it was given by this. Okay, so if you notice here, the rate law depends on NO2. It does not depend on CO. So this depends on this, and it does not depend on this. So this means that no matter how much you vary the concentration of carbon monoxide, it will have no bearing on how fast a reaction will be. Whereas if you vary the concentration of NO2 gas, since it's second order, it has a very big effect on how this reaction goes. We can now go look at basically what we have a mechanism. A mechanism is a step by step, and so here we have in this next bullet, we have two steps. So here's my first step, and then here's my second step. So what's happening is when we're starting to look at this on a molecular level, two NO2 molecules will actually collide with each other. So these two will collide, and after that collision happens, NO3 gets produced and an NO gets produced. And that happens in the first step. In the second step, that NO3 that was produced in the first step will now collide with a CO. And after that collides with a CO, it'll form NO2 and CO2. So, and this happens in the second step. So this is a two-step process. And there's a lot of information that can be given from if you start to see mechanisms. So in this reaction, they're saying that the first step is what we call a rate determining step. A rate determining step is the slowest step in a reaction. It determines the rate. So for example, with the peanut butter and jelly example, if you have a couple people helping you out, you can only make peanut butter and jelly sandwiches as fast as the slowest person. So if the slowest person is the person who's putting the peanut butter on the bread, then doesn't matter who else is on that in that little chain you have to wait for that person to get done with that. Same goes with this reaction. The rate determining step was determined by this step. All other steps depends on this step, and we call this the rate determining step. So in the second step here, we call this the fast step. This happens very fast, but the entire speed of the reaction is determined by the rate determining step. Some more very useful information is what we call intermediate. An intermediate is something that is formed then is consumed, and it never shows up in the overall chemical equation. So in this example, NO3 here is what we call an intermediate. It gets produced in the first step as and here it becomes a product. But in the second step, it gets consumed. So, so in this reaction, you never actually see it when it happens really, really fast as a reaction. And if you notice in your balanced chemical equation, you don't see that either. So you would never know that this intermediate exists for this. So we call this what we call an intermediate. Intermediates are always found in basically in the middle. It's always going to be a product in some mechanism and a reactant in another, and it will always disappear. One of the most useful information from this example of a mechanism is that you can determine the rate law from the slowest step. So if you notice here, in the slowest step, I have two NO2 molecules here. Well, look at my rate. I have NO2 squared. That is not by coincidence. You can always write your rate law from the slowest step. So the minute you see the slowest step in a reaction mechanism, you can immediately write your rate law from it. Because remember, rate is how fast a reaction goes. Your reaction can only be as fast as your slowest step. So since this is the rate determining step, you can actually write your rate law from the slowest step. Okay, so each step we call elementary steps. So it's a term for they use for a reaction mechanism. So when they say how many elementary steps something have, they're basically looking how many steps are there. And the rate for a reaction can be written in its molecularity. And molecularity is defined as the number of pieces that must come together to form this product. To help kind of define molecularity, basically it's when what is a molecule doing? Is it combining with other molecules? Is it breaking apart? So on and so forth. So for example, a unimolecular step is one where the reaction rate is first order. So let's say that we have this reaction, it is the slowest step. We have a molecule A and it's breaking down, decomposition into some products, doesn't matter. We can write our rate law immediately from this. Rate equals K to the A to the power of 1 because there's only one A there. So a unimolecular step is always going to be a first order rate law. A bimolecular step is when you have two molecules combining to form products. And the rate for that will be second order. So in this example, I may have two A's combining to form products. And we can immediately write the rate law if this is the slowest step as rate equals A to the power squared. In the example we had before, this was an example of that, two NO2 molecules. You can also have two molecules that are completely different react in A plus a B to form products, and we can write the rate law as rate equals A times B. So if you notice here, if these steps are the rate determining steps, you can always write the rate laws. There is what we call a trimolecular step. Whoops. Those are very rare to happen. So teramolecular means that it means all three molecules are combining or colliding with each other to form products. So just as some examples, if you have two molecules that are identical reacts with a third molecule which is different and they form products, you can write your rate law. So rate equals K A squared B. Overall reaction order is third order. What this means is that two of the same molecules of A and B are colliding at the exact same time. You can also write it as three different molecules, A plus B plus C, to form products, and the overall rate order will be 3. So again, three molecules are colliding at the exact same time to form a product. These are very rare because not only do the molecules have to collide, they have to have enough energy and they have to have the right orientation. So teramolecular steps are very rare. It's hard for three molecules to actually collide together at the same time with the right criteria. Usually reactions are first or second order or zero order for that matter. Okay, so a reaction mechanism a mechanism must satisfy two requirements. And the two requirements is that when you add the mechanisms together, some of the elementary steps, it must give the overall balanced equation for the reaction. And the second criteria is that the mechanism must agree with the experimentally determined rate law. So if somebody proposes a mechanism, you will check to see if it's a correct mechanism, if it satisfies these two things. If it satisfies these two criteria, it is a acceptable mechanism. So let's do this by example. All right, so here we have nitrogen dioxide reacts with fluorine gas to form 2NO2F. So this is definitely a synthesis reaction. They're saying that the experimentally determined rate law is this: rate equals K NO2F2. And we're going to see they give us a proposed mechanism. And the proposed mechanism happens in two steps. So here's step 1 and step 2. And the question is this an acceptable mechanism? Okay, well, we need to satisfy the first criteria, which is the sum of the elementary steps must give the overall balanced chemical equation by the reaction. So we're basically going to use some algebra here. We're going to add these two equations together and see if it forms this. So I have two NO2s, so I'm going to write 2NO2, so those form. I have an F2, and nowhere else will F2 cancel out, so I'm going to put F2. Okay, I do have an F here, and in this example, F is my intermediate. It gets produced in the first step and consumed in the second step. So just like with algebra, if you have two variables on the same side of the equation, you can cancel them out. So if you add these two equations together, F disappears. And then now, my product says I have two NO2Fs. All right, so I've combined these two formulas, two mechanisms together. I have an overall reaction. Is it this? Is it the exact same as this? And it is. So we have satisfied criteria number 1. It does. You do add them together, you do get the overall equation. The second criteria is that we have to determine if the rate law for the mechanism agrees with the experimentally determined rate law. So since this is the slow step, I can write my rate law from the reactants of this, so which I will do. Rate, oops, very hard to write with your opposite hand, equals K. Okay, I have NO2. There's only one of them, so it's NO2 to the power 1. And I have F2, and that's to the power 1 because there's only one F. That is my rate law that was written from this slow step. Is it the same as this? It is. That satisfies criteria 2. Since both criteria have been satisfied, this is this mechanism is acceptable. It is a possible mechanism for this reaction of these reactants and products. Alright, so I hope this helps give you an understanding of reaction mechanisms.